Good afternoon. In the lecture of today, we will talk about orientable surfaces. The first definition I need is the following. A normal vector to a regular surface S at the point P is a vector in R3 that is orthogonal to the tangent space TPS at P. In other terms, N in R3 is said to be a normal vector to S at P if the inner product of N with V is 0 for all vectors V in TPS. Instead, a unit normal vector to S at P is a unit length normal vector So the unique difference between the definition of unit normal vector and the definition of normal vector is the length. Or, equivalently, if we use the language of the definition 3.40, an orientation for TPS. So I suggest to see definition 3.40. Now let's suppose that we have a coordinate chart sigma defined on the open set U of R2 with values in V contained in S. Now with sigma Q equal P. We know that TPS is spanned by sigma u q sigma vq. So the natural idea for defining a unit normal vector to the surface S at P is the following. Take n P. This notation means the normal vector n at the point P as the cross product sigma uq and sigma vq, and we divide by the length of this vector. Please observe that this is one of the two possible choices. The other one is of course the vector minus n of p, and it is clear that none of it is special. Also because if you have a surface patch sigma, and here I am now assuming that u and v are the coordinates on u, then you can replace this surface patch by sigma hat uv just by making a simple change of sign of the second coordinate. And if you try to compute the unit normal vector n as we did here, instead of getting this vector here, you will get this one. Why? Because when you will compute sigma hat v at q, there will be a change of sign and consequently a change of sign of this vector. The next definition I need is the definition of vector field, tangent field, and normal field. A vector field on a regular surface S is a smooth map V defined on S with values in R3. In other terms, this is a map which assigns to any point of the surface a vector. It is called tangent field if Vp, this means the vector Sorry, I made a typo. I forgot the word field here. I'm sorry. So I was saying, what is the meaning of V of P? V of P is the value of this vector field at the point P of S. So this vector field is a tangent field if V of P is in TPS. For all P in S, instead it is called normal field if Vp is a normal vector to S at P for all P in S. So in other terms, if V of P is orthogonal to any vector in TPS. So suppose once again to have the surface patch sigma defined on the open set U over 2 with values in V contained in S. It is clear that the vector field on V defined by N of P equal sigma UQ times sigma VQ divided by sigma UQ times sigma VQ. This is a unit normal field on V. It is a unit because this is a vector of length 1 for any P, and it's normal because it's given by a cross product of two vectors which are tangent to the surface. So this normal field is not defined on the entire surface, it's defined only on V. Our next topic of interest is to determine whether or not it is possible to define a global unit normal field on the entire surface S. If the answer to this question is yes, then we call the surface S orientable. So we are ready to give the following definition. An orientation for a regular surface is a unit normal field on it. A regular surface S is said to be orientable if there exists an orientation for S. It's not finished. An orientable surface together with a choice of an orientation is called oriented surface. And the last definition I want to give is the definition of surface patch compatible with an orientation. A surface patch sigma. Okay, I don't need to specify the name of the surface patch for an oriented surface S is called compatible with the orientation if the vector field defined by the formula N of P equals sigma U cross cross sigma VQ divided by sigma U Q cross sigma VQ length agrees with the orientation for S. Okay, now let's see a few examples of orientable surface. So a regular surface is orientable if there exists an orientation for S. Orientation means unit normal field on it. So let's erase this part. So the first example is the plane. So let x, y in R3 be two linearly independent vectors let S denote the two-dimensional subspace of R3 spanned by X and Y. This subspace is a regular surface Y, so S is a regular surface because it can be covered by a single surface patch sigma defined R2 and given by this formula. So in other terms, sigma of uv is a linear combination of the vectors x and y. Now, what is a unit normal field on S? is given by this formula, of course. And what are sigma u and sigma v? Sigma u of q is just x, and sigma v at q is just y for any q in S. Sorry, for any q in R2. So we get that n of p is x cross y divided by x cross y length. And the reason why this is orthogonal to TPS, so n of p is orthogonal to TPS because TPS is the span of sigma uq sigma vq, that is the span of x and y. So x and y are the generators of the tangent space to the surface S, and by this definition I get that n of p is orthogonal to any vector in TPS. The next example is the level surface. So if f from R3 in R is smooth, and lambda in R is a regular value, then we know that S equal F inverse of lambda is a regular surface. Now we want to prove that this surface is orientable. In order to prove this, we observe that if lambda is a regular value, then for any p in F inverse of lambda, the gradient of f at p is non-vanishing. So the map p gradient of f p defines a non-vanishing vector field on f inverse of lambda, and if we divide by the length of the gradient, we get a unit vector field on S. It remains to prove that this is also a normal field. How to prove this? So let's check. It is a normal field. So what I have to prove is the following. I have to prove that for all vector v in TPS, I have to prove that the gradient of f at p multiplied by v is 0. Okay, the inner product of the gradient and v, this is equal to the derivative of f at p evaluated at v. But we know how to compute this kind of derivatives. This is equal to the composition, to the derivative of the composition of f with a curve on S having these two properties. The first one is that the initial point is p, and the second one is that the initial velocity must coincide with v. But it's easy to compute this derivative because f is constant on S, because S is f inverse of lambda, so f is equal to lambda. Consequently, this derivative is 0, and this proves that the gradient of f is orthogonal to any vector in Newtonian space, and this says that this vector field here is normal. Using this technique, you can prove that also the sphere is orientable. Why? Because any sphere can be seen as the level set of the function f of x, y, z equal to x squared plus y squared plus z squared. I leave the details to you. And now let's consider the last example, which is the one of the graphs. So we know that if U in R2 is open and F from U into R is smooth, then the graph G defined as a set of points of the form xy f of xy, where x and y are points of view, is diffeomorphic to U and the diffeomorphism, or alternatively the surface patch, is given by this map and we already saw that G is a regular surface. Because this is a surface patch. Okay, you can use once again the formula NOP equals sigma UQ times SVQ divided by its length. With U equal X and V equal Y to get a global unit normal field. And let's find out the explicit formula for it. So sigma x q with q given by xy is 1, 0 f of x, sigma y q is 0, 1 f of y, and the cross product sigma x q times sigma y q, this is given by minus f of x minus f of y 1. So NOQ is given by this formula, minus f of x minus f of y 1 divided by the square root of fx squared plus fy squared plus 1. It is also possible to prove that every compact regular surface is orientable This is consequence of a non-trivial result which can be seen as the three-dimensional analog of the Jordan curve theorem. So this is consequence of theorem 3.49, which says the following: if S is a compact regular surface, then R3 minus S, that is the set of points in R3 which do not belong to S, is exactly two path connected components. Their common boundary is S, of course, and one component is bounded, and called the interior, while the other one is unbounded and called exterior. Now, how to define a global unit normal field on a compact regular surface? This is easy. Just define a global unit normal field choosing interior pointing or the exterior pointing normal vectors. So this is also a second proof of the fact that the sphere is orientable. The sphere is compact. So here we have also that there are two possible choices for the unit normal field on the surface. This is not a coincidence, because we have the following lemma: if S is a connected orientable regular surface, then there are exactly two orientations for S. Each is the negative of the other. The proof of this result is easy. Okay, it's very easy to prove that there are at least two orientations. Okay, since S is orientable, then there are at least two orientations. They are and this is one orientation which exists because the surface is orientable, and the second one is minus n. So I mean you take all the vectors of the first orientation and you change their direction. Then let M denote an arbitrary orientation on S. We have to prove that M coincides with N or minus N, and then we'll finish it. In order to do this, we introduce an auxiliary function on S with values in R, given by the following formula. F of P is the inner product of NP and MP. So this is the vector field N evaluated at P, and this is the vector field M evaluated at P. For any P in S, you have that F of P is 1 or F of P equal to minus 1. So this is a function with integer values. defined on a connected surface. A surface is a set. You see the surface is a connected set, and then you use a proposition 8.19 from the appendix, which says that a function with the integer values defined on a connected set has a constant value, so implies f is constant. So this means that you have f of p equal 1 everywhere, or f of p equal minus 1 everywhere, and this means m equal n or m equal minus n. So this means that there are only two orientations. I would like now to observe the fact that we give two definitions of orientations. We have defined the notion of orientation of a surface, and in the past we gave a definition of orientation of a subspace of a finite dimensional space. There is any relation between these two notions? The answer is yes, if we look at the spatial finite dimensional space. Precisely, we have to look at the tangent space of a surface. And in order to understand what I'm saying, I need one definition. .51. So a diffeomorphism F defined on S with values in S prime, S tilde between two oriented surfaces is orientation preserving if for each P in S the map dfp from TPS into T of f of p s tilde is orientation preserving this is a definition we already gave, but I want to recall for your convenience. Yes, say, okay, this is definition, so C definition 3.41. A map a linear, let me check one detail, please. I think I need just a linear isomorphism. A linear isomorphism G between two-dimensional subspaces over 3 is orientation preserving and when I'm writing this I'm assuming that nu and nu tilde are oriented. If the following equivalent conditions are satisfied, one, if B is equal to V1, V2 is a positively oriented ordered basis of nu, then GV1, GV2 is a positively oriented ordered basis of nu tilde, and the condition number 2 is that the determinant of the matrix which represents G with respect to the positively oriented basis of nu and nu tilde is positive. Okay, so let's say it again. A diffeomorphism F between two oriented surfaces is orientation preserving if the map DFP from TPS TFP S tilde is orientation preserving, and orientation preserving definition is given here. Now we have simplification when the surfaces are connected, because this definition here says that I have to check that this map is orientation preserving for any P. So we have a lot of work to do if we want to check that diffeomorphism is orientation preserving. Instead, we have this proposition. (3.52), which says that a diffeomorphism between, no, let's write F from S to S tilde between connected oriented surfaces is orientation preserving if and only if there exists a point P in S such that DFP is orientation preserving. So why this result is a simplification? Because it says that if the surfaces are connected, then we have to check only that DFP is orientation preserving at one point. Just one point. Let's try to write down the idea of the proof. The idea of the proof is based on the part 2 of the definition 3.41, that is the definition of orientation preserving linear isomorphisms. Essentially, the idea is the following. Why it's enough to check that this map is orientation preserving only at one point? Because if you know that this is true for DFP at one point, then you know that the matrix representing DFP as positive determinant and the unique detail we have to understand is that why you cannot have a change of sign. You cannot have a change of sign because the determinant of the FP can be considered as a continuous function on the surface. The surface is connected and second remark, the determinant is always different from zero. So we have a continuous function which cannot be zero, which is positive at one point on a connected set. So this ensures that the determinant is always positive. And this means that this map here is orientation preserving. And that's all. Now let's present an example of non-orientable surface. This is known as Mobius strip. Model of this object can be constructed using a strip of paper, gluing its ends after a twist. It is possible to prove that this surface can be parametrized by the map sigma uv equal to cosinus of u times 2 plus v sinus of u over 2 sinus of u 2 plus v sinus of u over 2 v cosinus of u over 2. I would like to present briefly the explanation of the origin of this formula. The idea is the following. Consider a vertical line segment denoted by B, parameterized by the map BV equal 2, 0, V, with V in minus 1/2, 1/2. So essentially, if we try to make a picture, what you get is for example this. This is B. Now, in order to get the Mobius strip, you have to write down a map which represents a rotation of B around the z-axis, while at the same time B rotates this way. The idea for constructing this map is that if, for example, this is an angle equal to u, which is this variable, then B will have rotated by an angle equal to u over 2. Why u over 2? Because I told you that B must rotate around the axis of 2 pi, and at the same time B must rotate this way, so it has to make 180 degree turns. This means pi, which is half of 2 pi. Now it's possible to parameterize this rotation by u over 2, and this is given by B u over 2v, which is a sort of generalization of this one, by 2, 0, 0 plus v times sinus u over 2, 0 cosinus of u over 2. The reason why there is no y here, sorry, there is a y component which is 0, is that this segment rotates in the xz plane. Now we have to compose this rotation with a rotation around the z-axis. And you know what is a matrix? Matrix representing a rotation by u around the z-axis. This is given by AU equal to cosinus of u minus sinus of u, sinus of u, cosinus of u, 0, 0, 0, 0, 1. Then we have to compose this map with this map. How to do this? Simple. You take the rigid motion LAU and you compose it with BU over 2. And this is what we call sigma. The map I wrote here and I erased. Okay, now let's prove the following fact. The Mobius strip is not orientable. Consider the following parameterizations: sigma I where I is equal to 1 or 2, where U1 is the set, and U2 is a set defined this way. These two maps here are the restriction of sigma. So sigma I equal restriction of sigma on UI. Now, it's possible to prove that these two patches cover S, where S is a Mobius strip, so they cover S. And let's denote by N1 and 2 the unit normal fields induced by sigma 1, sigma 2 on V1, V2. V1 and V2 are the image of sigma, of U1 and U2 by sigma 1, sigma 2. What is the meaning of this expression? This means that you use the formula N of P equals sigma UQ cross product sigma VQ divided by its length, sigma U Q VQ. Okay, it's possible to prove that V1 looks like more or less like this, and V2 looks like like this. Instead, the intersection V1 intersected V2 looks like this. And it is given by the union of A and B. So let's say that A is this one, and B is given by these parts. Okay, now let's suppose by contradiction suppose that there exists a global unit normal field on S. I call it N. Since V1 is connected, then N is equal to N1 or N is equal to minus N1. We can suppose that this is true, otherwise replace N by minus N. Then since V2 is connected, then N is equal to N2 or N equal to minus N2. We can suppose that this is true, Otherwise, we replace N2 by minus N2. If this is true, I have to write something. If this is true, N2 agrees with N1 on A union B, because A and B lives in V2. But we have a problem. N1 and N2 agree on B, but they disagree on A. Why this is true? Because if, for example, n points, let's use a blue color, if n points and 1 points this way, for example, and n2 points this way, you have that they agree on B because they points outward, and they disagree on A because on A they point inward, N1 point inward, and on this part it points N2 points outward. So it's true that N1 and N2 agree on B, but they disagree on A. So it is not true that up to, if you make a change of sign, like I wrote here, you can make this true. So this is a contradiction. So contradiction implies S does not admit a global unit normal field. Okay, I think that's all for today. Thank you for your attention.